Okay, team. Today we're going to talk about water distribution system design. Specifically, how can we design a water tank to supply sufficient pressure and flow to a community? So we're going to introduce a software, EPANet. It's a pipe network modeling program. It can model various sized pipe networks from teeny tiny to a whole city. And then we're going to use EPANet and kind of a template for a community to design a water storage tank to meet various system requirements for pressure and flow rate under different critical scenarios. So I have a link to this video. This is a practical engineering video about water towers, how they work, why we have them. So I'm not going to play that here, but I have it linked and I would like you all to watch that for some more context on water towers and water system distribution design. A little bit about EPANet. I've got a link to the website on Canvas, and we'll be using it both for homework and for lab number 2, where you're doing this tank design. It is an old school, an oldie but a goodie modeling software, and it can model water quality, it can model flow, energy loss, pressure, in varying complexities of systems. And we will have a separate video that gets into how to use EPANet and how to get started with it, both for the homework and for the project. But I just want to introduce it briefly here, and really great, solid software that can incorporate reservoirs, water towers, pumps, and then pipes and demands throughout the system. We'll be running EPANet under steady state conditions. So that just means that we're going to assume that the inputs and the outputs are constant. EPANet can do a lot of different things. So under steady flow for a given demand scenario, so for example, maximum daily demand or maximum hourly demand, it can determine flow rates in pipes, which are called links, and calculate the pressure at junctions or nodes. We can put in, like I said, tanks, reservoirs, pumps, and valves. It will compute friction losses using a number of different methods. We'll be using Darcy-Weisbach, but it can use Hazen-Williams and Manning's. It can also compute minor losses. We're going to be ignoring those in our lab, though. Some of the scenarios that you can run are, for example, what kind of pipes can I use? How narrow of a pipe, how small of the diameter of a pipe can I use to get the desired flow and pressure at different points in the system? You can also evaluate different pumping schemes and energy costs over time. And it's also useful under unsteady flow conditions where you're tracking demand, say that demand's changing hourly over a day, and looking at where you might have critically low pressure and discharge times or high velocity times under high demand scenarios, and optimizing your system to work for both steady state and peak conditions. Let's get into lab number 2. Like I said, you're going to be designing a water tower, a tank that is above the ground. And that tower has 2 design parameters: diameter for the tank and height of the bottom or the invert of the tank above the ground to deliver sufficient flow and pressure to this community. And here's just a little schematic of the community. We've got a storage tank that's basically a clear well or reservoir that's got treated water. Water's pumped out of that into the storage tank. And then the storage tank is what provides that consistent pressure and supply for the community over the course of a day or multiple days. So the community is composed of these blocks that have different kinds of homes. We've got low density residential, that's these LDR homes, medium density, and we've got apartments, we've got high density residential, and then we've got commercial and industrial. Now, I am providing you all with a table that has the demands for each of these blocks. So in a previous homework assignment, we looked at calculating the demand, average daily demand, maximum daily demand, et cetera, for the same community. And you all came up with some volumes for the tank. So we're going to use that information and kind of give you some volumes to work with based on these different demands, including fire demand. And then you're going to focus on designing the storage tank. So here are the scenarios that you're going to use to design this tank. And there's three of them. The first one is a low pressure, sorry, a very, see, maximum daily demand flow. So high flow demand. And then we also have fire flow. So what we're trying to do is say, okay, how high does this tank need to be so that we have sufficient pressure in the system greater than equal to 20 psi at all the nodes in the system. We have maximum daily demand, so a lot of flows moving through the system, a lot of velocity. So this is kind of low pressure conditions. And then we've got a fire. And it's just one fire that could be happening anywhere in the community. So you need to figure out how high the tank should be so that this kind of extreme scenario, the tank is nearly empty and we've got a fire and everyone's watering their lawns. That's scenario number one. That's going to establish the minimum bottom elevation of the tank that we don't want to go below. Under the next scenario, these are kind of like normal conditions. We've got no fire, okay? So no emergencies. We also have maximum hourly demand. So big draw from the community on this. And under those conditions, we want to have at least 35 psi everywhere in the system. So now you're going to adjust the height. We're not going to go down, but we could go up, and we're going to adjust the diameter as well. So a wider tank will have a shallower depth for a given volume. Finally, we're going to have a maximum pressure scenario, and that's going to be refining the tank diameter and height. And this is going to be where we have very low demand on the system and the tank is full. We want to make sure that under those conditions, we're not going to burst anyone's faucets or pipes. We want to make sure the pressure is low enough so that we don't cause any damage in the system. All right, just a little bit about the community. We've got these blocks here, and note that the blocks don't necessarily follow the roads. So the idea here is that the water supply is going along the roads and it's providing water to both sides of the street. So just kind of keep that in mind when you think about the blocks. They have an ID and that we've got both sides of the street. Kind of think of this as the alley for a block. I'm going to give you the EPA network already, and it's going to have the same IDs for the nodes. So you can see here this node has an ID of 115. We'll go back and note that this is block 115. So when we see a table that has demands for average daily, maximum hourly, you're going to note that each block is going to have that demand. We're going to change the demand at these nodes. So 115 all the way down to 515. That's block 515 over there. Block 570 for the warehouse. There's 570's node. So this is the node that's supplying water to that block. These nodes are where we're going to have demand. And so you're going to actually put a value in there, cubic feet per second, of water leaving the network. That water is going into the warehouse. It's going to go out into the sewer. It's leaving the pressurized water supply network. So water is coming in here at the tower, and then each of these nodes is going to have a different demand based on the makeup of the block. All right, let's talk about these scenarios in the storage tank, the water tower. We're going to divide the water tower up into different volumes. The bottom volume is going to have the fire volume, which will be the volume needed to put out the biggest fire, one biggest fire in the community. You remember calculating that for, I think it was homework 2. And so I'm going to provide you with a table with updated numbers for that. It'll also have an emergency range, which is going to be a percentage of the normal operating range, which I'll talk about in a second. The normal operating range is going to be based on those average daily demands. Well, in this case, maximum daily demand. So normal operating range, maximum daily demand for one day. And then here we've got the maximum fire volume, one fire plus 25% of maximum daily demand. So that's going to be kind of a safety factor that we'll have in there because none of our calculations are perfect, right? All right. I've got a spreadsheet that you can use to help in your calculations. You don't have to use it, but maybe it's going to be helpful. We'll talk about it as we go. So here's that table of volumes. Here's your maximum daily demand volume, the emergency volume, which is 25%, the maximum fire volume, one fire that you're fighting for the biggest fire that's potentially out there, sum them all up, and here we've got the volume of the tank in cubic feet. All right, so for scenario one, remember, we're going to choose the bottom elevation of the tank. This is a parameter that you can assign, and it's just elevation above the ground. We're going to assume the ground elevation is 0. Um, and you're going to adjust that. You can also, the other parameter you can adjust for the tank, actually there's 3 of them, the bottom elevation, the depth of water for a given volume in the tank itself, and then the diameter. So we're going to start with a diameter of 80 feet, which I'll talk about in a second. You are going to assume that the tank is about dry. We have to put a number in there for the model run. So we're going to put a thousandth of a foot for the depth. And then we're going to adjust the elevation so that we get greater than 20 PSI under summer maximum daily demand conditions at all those nodes. So you will go into the model and assign those values at each node. Okay, maximum daily demand, initial water depth in the tank, thousandth of a foot. And then we're going to put a fire on the nodes. You're going to find which fire causes the lowest pressure in the system. Okay, so you're going to try a few of those. And I'm going to give you a hint. You just need to think about which one of these blocks and go back to that homework 2 assignment and think about which one of these blocks is going to have the biggest fire demand, the biggest flow rate for a fire. So that'll help you zero in on which nodes you want to think about. And another hint is that the farther away you are in the system from the supply, the lower the pressure is going to be due to major losses. So you're going to be focusing on this sector. You don't have to do a fire at every node, okay? This table here will help you track that. So we've got all the different nodes, what's the fire demand, and what's the minimum pressure in the system given the fire demand at these nodes. I'm not saying you've got to do a fire and run the model however many times. There are nodes. So just focus on the ones you think are going to be the biggest. Put a fire demand on that node on top of the maximum daily demand, and then just track what's the minimum pressure in the system. Okay, so here's just an example of that. And I've got the visualization of the pressure that's in blue. You can see that over here we've got 51 PSI, and over here we've got 32. So you're going to be adjusting that tank elevation so that you get 20, let's say, at the lowest pressure node where the fire demand is. So you can track both the demand and the pressure at the nodes using a node table. And I'll tell you how to bring that up on the EPANet video. So you'll be able to pull these tables up, and under a given model run, you'll be able to see, okay, here's my demands. Let me just double check, make sure those make sense from what I put in. And then here are the pressures. You also have a link table. So the node table are the demands and pressures. The link table is going to give you flow rate, velocity, head loss, etc. Now on to scenario 2. This is under operational pressure, that greater than 35 PSI everywhere in the system. You're going to go into the system and enter at the nodes the maximum hourly demand, no fire. In the tank, we're going to have water that includes the fire volume and 25% of maximum daily demand. Okay, so we're going to assume we're at the bottom of the normal operating range, and we just have that fire and emergency volume in there. We're starting with a diameter of 80 feet, and you're going to have to calculate what is the water level in the tank, because EPA Net's not going to solve that for you directly. What's the water level in that tank given the volume and given the tank diameter? So it's just a cylindrical problem, cylindrical geometry problem. So you'll go to the tank, you'll put that initial water level in the tank. Note that because we're operating at steady state, EPA Net's not going to update the depth in the tank. It's just going to keep it at a constant value. You have put in the maximum hourly demand at each node, and then you're going to run the model. No fires, and you're going to try to find out where we have uh, less than 35 psi, and then you can either or move the tank bottom elevation up or adjust the diameter. I'm going to suggest just adjusting the diameter at first to see if you can get that greater than 35 psi everywhere, but you can also raise the tank elevation if you want to. So this table can help you with those calculations. Again, we'll start with a diameter of 80 feet. You then put your volume numbers in there. So for this calculation, we're interested in the non-fire emergency volume and then the fire volume. And then in a subsequent step, you can calculate the height of water in the tank based on those volumes and the diameter. So it's just going to be an equation, the cylindrical equation, and you're solving for height of the cylinder based on the diameter and the volume. Okay, so now you run the model, see if you've got 35 psi or greater. If you don't, then you're going to adjust the diameter. And you can narrow it, right? That's going to make the water taller. You can widen it. That's going to make the water shallower. And if this equation here, right here, for the height of the water is a function of the diameter, then you can just adjust the diameter, and then this height will adjust. You put that height back into EPA Net, and then run the model again. All right, last scenario. This one is going to be where we've got a full tank. So the full volume is in there. You've got your diameter and height from the last scenario. And now you basically kind of need to refine everything so that you don't exceed 100 psi in the system. So a question to ponder is, where will the pressure be the highest in the system and under what condition? So let's just look at this. You're going to use that cylindrical volume formula to find the height of the water given your diameter and the volume of the full tank. And then think about which node is going to have the highest pressure in the system. Well, we know that the farther away you are in the system, the lower the pressure, right? So it's probably going to be one of these two nodes that's going to be the highest pressure. You're going to add average daily demand to each of these nodes from winter. So that's going to be the lowest demand the system would have, would experience. And then you're going to run the model and look at pressures in the nodes. Remember, don't violate the conditions from steps 1 and 2. You want to save your model for each scenario and just kind of have a separate copy of it so you can always go back if you kind of get too far down the road and mess things up. Don't violate those conditions. Don't go below the minimum elevations for step number 1, and make sure you still have that 35 psi that's valid from the previous problem. Okay, you can calculate the pressure at the bottom of the tank in psi, assuming hydrostatic conditions. So remember, pressure is equal to height times gamma, and that'll help get you started. You can then calculate the maximum water elevation in the tank from Z bottom plus D full, and that will then allow you to calculate the maximum pressure in the pipe network, which is under full conditions. So the Z bottom up to the bottom of the tank plus the elevation in the tank when it's full. All right, so that's going to be a good guess. You can kind of do some just spreadsheet design to say, okay, under hydrostatic conditions, can I get close to 100 psi with my Z bottom and diameter? All right, just to review, step number one fire, one big fire in the system. We got to keep pressure greater than or equal to 20 psi, and we've got our maximum daily demand in the system. And the tank is basically empty. We'll run one fire at a time across the nodes, and I'm not going to say all nodes, but just the nodes that you think could be resulting in the lowest pressure. Farther away in the system, bigger fire volumes or flows. So that in that scenario, you're raising the bottom of the tank elevation to meet this condition, just the elevation of the tank. Step number two, maintain at least 35 psi under normal conditions, no fire, and maximum hourly demand. The volume in the tank is going to be fire plus emergency volume, and you're calculating the depth of the water in the tank using the cylindrical equation. In this scenario, you're going to adjust the tank diameter and or raise the elevation to meet those conditions. Finally, you want to make sure that the maximum pressure in the system is less than or equal to 100 psi at all nodes. And this is when the tank is full. You can adjust the tank diameter and lower the bottom elevation, but don't go below the elevation for step number one. And you might want to go back to step number two with the dimensions, the diameter and the elevation of the tank, just to make sure that this is still valid. Those design criteria are still valid. All right, that's it. Good luck in your modeling.